Okay, so now let's apply those formulas. So let's find the sum. So there's a couple ways you could do this. I'm not going to show you every single one in great detail, but I'll describe them to you. You could type this in the calculator, exactly how it looks, and it'll find the sum for you. You could plug 0 in and get 5, and then plug 1 in and get like 5 times 0.3, which is like 1.5. Alright, and then keep going until you get to the fifth term and add all those up. That would also work. Alright, we're going to use the sum formula, which was the first term times 1 minus the common ratio to the nth power over 1 minus the common ratio. Because this is geometric, I could tell it's geometric because the nth term formula looks like it's exponential. So when that happens, that means it's geometric. Now, a couple things with this formula. For one, this technically isn't the first term in regards to like you plug 1 in for n. It's the first term as like this number here. Like if you were to write out all 6 terms, because this does have 6 terms. It's the 0, first, second, third, fourth, and fifth. That's 6 numbers because you're starting at 0. Really, you would plug in the 0th term here. If this number was like 3, then you would do the third term there. Okay, so it's not always a sub 1 that goes here, but it is always the first term. So the first term is going to be when we plug in 0, so we're going to get 5. So we get 5 times 1 minus the common ratio. Now if you're not sure of the common ratio, you could plug in 0 for n and 1 for n, and then divide the first term by the 0th term, or plug in 2 for n and divide the second term by the first term. Or if it's like an exponential type of expression, that number getting raised to the nth power is going to be the common ratio. So it's going to be 0.3 to the nth power. So that's how many terms there are. So it's not necessarily this number, 5. It is if it was n equals 1, but that's not the case. So again, we have the 0, the first, the second, the third, the fourth, and the fifth term. So that's really 6 terms that we have. So n is going to be 6. And then put that over 1 minus r, and then type that in the calculator, and we get our sum. Okay, I'm having a little trouble sharing the calculator on my screen. I'll look into that after I make these videos, but I was able to just project what I typed in. So you could see that you could do that either way. Use the formula or just use summation notation. But you do want to know how to use the formula because certain questions you need to use it, like if you're solving for the ratio and you know the sum or something like that. So don't rely on this bottom part here, but you should know how to do this both ways. Okay, one really cool application of infinite series is to use it to write decimals as fractions. So a little fun fact, if you ever have a repeating decimal of 2 digits that keep repeating and they're multiples of 9, like 0.09, 0.09, or 0.18, 0.18, or 0.27, 0.27, or like this, that means it's something over 11. Alright, and that's just a little fun fact that I learned being bored in class without a cell phone back in the 2000s and playing around with calculators instead as a distraction. So we could prove that this right here is equal to 4/11ths, and we could do that using an infinite sum formula. So the first thing I'm going to do is write this out as a series. So 0.36 plus 0.0036 plus, my stylus is breaking, my iPad's breaking, this is virtual teaching is falling apart right now, but we're going to get through it. Alright, bang, there it is. So it's going to follow that pattern. Now this is actually a geometric sequence because we have a first term, it's 0.36, and if you divide any 2 consecutive numbers, like this divided by that, you see that the common ratio is 1/100th. So if we use the infinite sum formula, which is the first term, over 1 minus r, we get 0.36 over 1 minus 1/100th, which we'll write as 0.01. Alright, as a decimal, that's 0.36 over 0.99, which is 36 over 99. 9 goes into 36 4 times, goes into 99 11 times. Bang. So we just wrote this repeating decimal as a fraction, and you can use that kind of logic to write any repeating decimal as a fraction.